Hello class. This recording is for lesson 6, and in this lesson we will be talking about capacitors and inductors. So this is quite a few shifts from our previous discussions because in our previous lessons we've tackled only resistors. So far we've only learned circuit techniques and resistors. So in this lesson, we let us introduce another two of the most important and practical types of circuit elements, which are capacitors and inductors. You can almost see them in every circuit board that you can find apart from resistors. So in the image that you are seeing, we have three basic circuit elements. We have the resistors, which are those ceramic stuff that you can see in stripes, and then we have the capacitors, which are those ceramic stuff again, represented in solid colors, which is in this case red and blue. And then we have the inductors, which are represented in a solenoid or a coil of wire. But apart from these three basic elements, we also have transistors, this gray like bus like stuff that has many legs in it connected to the circuit board. They are also important basic circuit elements that you can find in any circuit board. So capacitors and inductors are quite leveled with resistors. There's nothing that we have to be afraid of because the previous circuit techniques that we have discussed from previous lessons can still apply for capacitors and inductors. So that's a good thing. So this lesson has two goals. So at the end of the lesson, we are expected to, number one, understand what a capacitor and inductor is and how it works around the circuit, its functions and things like that. And the second goal would be to expand our circuit analysis techniques that we have learned from resistors to capacitors and inductors, with of course just a very few tweaks, nothing very difficult. In terms of difficulty, I think the previous lesson about circuit theorems are the most challenging in terms of circuit analysis techniques, but then we've only tackled resistors. So let us upgrade our learning by tackling capacitors and inductors as well. Capacitors and inductors are passive linear circuit elements similar to resistors, so they are just leveled. Unlike resistors, which dissipate energy, capacitors and inductors would store this energy and release it at a certain time. So this is one of the main difference between resistors and capacitors and inductors, because resistors basically resists the flow of electricity, and the energy that they get from resisting would be dissipated as heat. So if you can notice that in when you have prolonged use of your electronic device, it becomes hot. So that's just a dissipated energy in form of heat. Uh, so unlike resistors, capacitors and inductors would store this energy, and then the moment the mode that capacitors and inductors release this energy is dependent on certain conditions within the circuit diagram itself, such as when the when the circuit board rather reaches a certain voltage or current. Some capacitors and inductors would be actuated to release the stored energy. But even though they store energy, capacitors and inductors do not store this energy in the same way a battery does. So a battery is an electrochemical component. Capacitors and inductors are basically just tweaked has a very simplified tweak circuitry inside, not really electrochemical in nature. So you might ask, what are capacitors and inductors for? So capacitors and inductors are important because one, as I said, they store energy. So energy storage within a circuit board is important in order to for it to function at at many events or at many circumstance, not just on and off kind of thing or situation. So capacitors and inductors would store energy and then release it in order to actuate another segment in the circuit board. So that's the first importance. That's the first reason why they are important. And the second reason is that capacitors and inductors resist abrupt changes in current or voltage. So in a way, capacitors and inductors act as regulators. They store and they release energy, but they don't just release energy at any point in time. They release energy only at a certain when certain conditions are met in the circuit board. So they act as regulators. So first off, we have capacitors. So capacitors is a passive element designed to store energy in its electric field. Beside resistors, capacitors are the most common electrical components. Capacitors are used extensively in electronics, communications, computers, and power systems. And you can even see larger capacitors in electric fans. Usually, electric fans would not work if there is no capacitor connected to it. So, in the case of an electric fan, the capacitor is important in such a way that it gives the motor the necessary amount of energy in order to start. So, that's the importance of capacitors. They act as buffers of energy in a circuit board. A typical construction of a capacitor is indicated below. So as you can see in this image, we have two plates, and in between these two plates is a material which is called a dielectric material. If a resistor has a value of resistivity rho, a dielectric of a capacitor has a value of permittivity, or I don't know what you call that symbol. I just forgot. I'm sorry. So typical metal plates are made of aluminum. So these metal plates, they are usually made of aluminum, while typical sandwiched or dielectric materials include air, which means there's nothing in between them. Sometimes they are made of ceramic, paper, or mica, and the material of the dielectric would depend on its function. So there are some dielectric materials which are meant for smaller capacitors, and there are dielectric materials which are more appropriate for larger and more heavy-duty capacitors. But its basic construction is the one that you're seeing in this diagram right now. So in a circuit thematic diagram, capacitors are usually symbolized as just what you're seeing here below. Usually, for simplicity, they are just represented by two parallel lines. So whenever you would see this diagram in which there is one straight line and there's one curved line, the straight line usually represents the positive end of the capacitor, while the curved line represents the negative end of the capacitor. But for simplicity, especially when you're just drawing the capacitor in a diagram, you can just use two parallel lines and then indicate the polarity for simplicity. So how does a capacitor work? When a voltage source V is connected to the capacitor, the source deposits a positive charge on one plate and a negative charge on the other, as what you are seeing in the diagram below. The capacitor then stores this electric charge. So this electric charge, both positive and negative, would remain on the two plates of the capacitor. So that's the basic operation of how the capacitor stores energy or stores electric charge. The amount of charge stored in this capacitor is proportional to the voltage applied, meaning that the higher the voltage, the higher is the charge stored. This is represented in the formula below. So we have charge represented by Q and voltage represented by V, and then the C would become the constant of proportionality, which is the capacitance, which is the unit of measure for a capacitor. So we have resistance for resistor, we have capacitance for a capacitor, which really is a no-brainer. It is measured in terms of farads. So I think you're familiar with Michael Faraday. So this is in honor for Michael Faraday, but we won't talking about him here. The current voltage relationship of a capacitor is represented in this diagram. So in order for current to exist, the voltage applied must change with time. So this is not just a constant voltage. We are talking about rate of change, remember, in derivatives, in differential calculus. So the voltage that we are talking here changes with time. But what makes it challenging is that in a DC circuit, the voltage doesn't really change with time. So in a DC setup, the dV/dt doesn't have a slope. It's just a horizontal line. So the caveat of a voltage that changes with time, this is only applicable for AC, not DC, and we will discuss that next. Later on. The energy stored in a capacitor is given in this formula below. We have C for capacitance in farads, V is the voltage applied across the capacitor, and the power or the energy is in terms of joules. So that's how we measure the energy stored in a capacitor. So these are the common appearance of capacitors. So we have smaller ones on the left and then larger ones on the center and on the right. So these smaller ones, you would commonly see them in circuit boards, while larger ones would be used for more heavy-duty applications such as operation of an electric fan. So there are three important characteristics that we need to learn for a capacitor. Number one is that we need to contemplate on this formula number 2, in which the current would only exist if the voltage applied changes with time. So that's our first condition. Now the first characteristic is that there is no current through a capacitor if the voltage applied across it does not change with time, which is exactly the property of a DC voltage. Therefore, a capacitor is an open circuit to DC, and we will learn how that open circuit would look like in our circuit analysis when we solve a problem. So just to recall from equation 2, this is our equation 2. The derivative of a constant is 0. So in a DC environment, the voltage is constant, and when you derive that, it becomes 0. So a capacitor is therefore assumed to be an open circuit to DC. So second characteristic is that even if current through it is 0, the capacitor can still store energy when the voltage applied across it is constant by storing charge Q. So we need a voltage in order for a capacitor to store charge and therefore store energy. So because they are physically not connected, there won't be a current that will flow across the plates, but there will be charge stored in each of the plates. The third characteristic that we need to remember is that it is impossible to change the voltage across a capacitor by a finite amount in zero time, as this requires an infinite current through the capacitor. So, just for analogy, a capacitor resists an abrupt change in the voltage across it in a manner analogous to a way a spring resists an abrupt change in its displacement. So the capacitor resists abrupt change, and that's the second reason, which I previously mentioned, that capacitors and inductors are useful as regulators in a circuit board. So these are the basics of a capacitor, and let us dig in more by solving a sample problem and particularly observe how to solve a circuit problem that involves capacitors. So what you're seeing right now is a sample problem which has two capacitors, and it tells us, or it asks, that under DC conditions find the energy stored in the capacitors. So as previously mentioned, under DC conditions our capacitors would be assumed as an open circuit. So the first step that we need to do is to open circuit the capacitors. So let us just redraw the diagram. We have the voltage source. We have this resistor network over here. We will assume that to be an open circuit. The 20 microfarad capacitor. By the way, usually capacitors, especially in our circuit analysis, they are usually in a very minute values, such as microfarads. So don't be surprised if all our capacitors would be in microfarads. So we have another open circuit here for the 30 microfarad capacitor. We have a resistor on top, and then a resistor on the side. So this is 1 kilo ohm, 3 kilo ohm, and 6 kilo ohms. So simplifying further, this becomes basically a series circuit. We have 50 volts, we have 1 kilo ohm, we have 3 kilo ohms, and 6 kilo ohms. So as simple as that. What we can learn from circuits in series is that the current across the circuit is the same. So we can solve now for the current. I is equal to V over R is equal to 50 volts plus 1 kilo ohm plus 3 kilo ohm plus 6 kilo ohm for a total of 10 kilo ohm or 10,000 ohms. The current then is equal to 0.005 amperes. So what we're gonna do next is we have to calculate branch currents and or parallel voltages. Of the capacitors. So how exactly are we gonna do it, since we are assuming our capacitors as an open circuit? Don't worry. So let me draw here our V1. So this will be our this will be for the voltage across our first capacitor, and then our V2 for our second capacitor. We can solve V1 and V2 if we solve the voltages that is parallel, the voltages on the resistors parallel to these open circuits. So we have, for example, for V1 we have 3000. The resistor that is in parallel to this voltage is 3000 ohms or 3 kilo ohms, and then the current that we've solved here, the current I is 0.005 amperes. That leaves us V1 as 15 volts. So the way that we solve V1 is we basically solve the voltage across this resistor network over here. So that's V1. And since we've learned that in parallel circuits voltages are equal, we can just solve the voltage by looking at its parallel branch. And the same would be true for V2 in this in the 6 kilo ohm resistor. So now let's solve for V2. We have 6000 ohms or 6 kilo ohm times 0.005 amperes. That's very small. We have 30 volts. So now that we have solved V2, let us just make it clear that voltage across the 30 microfarad capacitor is equal to V1, since you can clearly see that they are parallel. But for the voltage across the 20 microfarad capacitor is equal to V1 plus V2. So why is that? The immediate parallel of this capacitor here are these two. So that can be a bit tricky at times, but please do remember, when we open circuit a certain element in a circuit diagram, we need to immediately determine its adjacent voltages. Now let us solve for let us solve or calculate for power. So we have P as our power. We have P1, the power, that is the energy rather. Let me change that. So this is what the textbook has been annotating for energy. They are represented by P. So let us solve for the energy that is stored in this capacitor over here. As what we have learned in the handout, the formula for power is 1/2 CV squared. So 1/2 the capacitance of 30 microfarads, 30 times 10 to the negative 6 farads. So that's the scientific notation for micro. and then we will multiply that with V1. So our V1 is 15 squared. So our P1 then is equal to 0.003375 or 3.375 millijoules. So box our final answer. It would be helpful, class, if you would use scientific notations or use the proper notations for micro, milli, in order to make our final answer more presentable. Then for P2, we have P2 is equal to 1 half CV squared. We have 20 times 10 to the negative 6 farads, and then we have V1 plus V2, we have 15 plus 30 all over squared. Calculating that, we have P2 20.25 millijoules. So there you have it, our energy for the two capacitors in this network. So this is a sample problem from the textbook. The textbook doesn't provide a solution, but it does provide a final answer, and these two are correct. So that's so far for capacitor. Going back to our handouts, the next on the list is inductors. So an inductor is also a passive element consisting of a coil of conducting wire, as shown in this image, designed to store energy in its magnetic field. So they are quite similar with capacitor. So like capacitors, inductors also find numerous applications in electronics and power systems. They are used in power supplies, transformers, radios, TVs, radars, and electric motors. But one example that comes into my mind is inductors are widely used for AM transmitters and receivers. In short, they are used for radios. So for telecommunications. And what the inductor does is that it filters out the signal. So inductors are very important in order for us to hear the sound on the radio very clearly. So we owe that to the inductors. Any conductor for electric current has inductive properties and may be regarded as an inductor. So in reality, class, you can create your own inductor by just coiling a wire that has a current in it, a current carrying wire. But in order to enhance the inductive effect, a practical inductor is usually formed into a cylindrical coil with many turns of conducting wire. So that's it. You can just make your own inductor. That's what it's basically said. And in a circuit thematic diagram, inductors are symbolized as just a coil. They are quite similar with resistors, and I bet you should not mistake them. You should not be mistaken for them as resistors because they are represented by coils. So just a very simple, like 4 coils, just to be specific. And yeah, please don't mistake inductors for resistors. So how does an inductor work? When a current is allowed to pass through it, inductors oppose the change of current flow. It then stores this energy in form of a magnetic energy. So inside the coil and even outside, there is a magnetic field that is formed by the orientation of the current carrying wire. We have learned in physics that a current carrying wire has an induced magnetic field in it. I think that is Faraday's law, but I can't be sure. So once it's coiled, the magnetic field and the energy in it will be stored inside the inductor. Inductors are measured in terms of inductance, represented by letter L. It is measured in terms of henries. So if capacitor is measured in capacitance in terms of, what was that again? In terms of farads. So we owe that from Michael Faraday. Inductors are measured in terms of henries. So that Henry is another scientist. I can't really remember his full name, but the measure for inductance is owed to him. So as I previously mentioned, you can make your own inductor by just simply coiling out a wire. And in order to come up with at a certain value of inductance, this is the formula. Formula number 4. We have L is equal to N squared. Then we have the permeability times the cross-section area of the coil, all of which divided by L, which is the length of the coiled wire, not the length of the wire as a straight wire, but the length when it is coiled. So if a resistor material has a value of resistivity and the electric of a capacitor has a value of permittivity, then an inductor core has a value of permeability, which is represented in mu. So the voltage current relationship, which the capacitor also has and the inductor also has, this is represented in this diagram. In order for voltage to exist, the current applied must also change with time. So if we recall from capacitor, in order for current to exist, the voltage applied must change with time. The reverse is true for inductors. In order for voltage then to exist, the current applied must change with time. And again, a current that changes with time is found in alternating currents or AC, but not in DC. So that's we will further discuss that over here. But for now, let us learn that the energy stored in an inductor is 1/2 is equal to 1/2 Li squared, in which L is the inductance and I is the current applied to the inductor. And then once again, similar to capacitors, energy stored by inductors are measured in terms of joules or J. In this image that you are seeing are just physical appearance of common inductors. So you can on some larger inductors, you can clearly see that they are a coil of wire, some of which has a core like a metal or a magnetic core inside it, while for other smaller uses they are quite similar with resistors because the coil inside is made to be compact. So yeah, once the next time that you can encounter an open circuit board and so you can see this these elements similar to what you're seeing in this image, then you can suspect that it is an inductor. So there are 3 important characteristics of an inductor. First off is the voltage current relationship, that in order for voltage to exist, the current applied must change with time and that is not possible within a DC. So there is no voltage across an inductor if the current through it is not changing with time. Therefore, an inductor is a short circuit to DC. So if a capacitor is an open circuit to DC, an inductor then is a short circuit to DC. And the second characteristic is that energy can still be stored in an inductor even if the voltage across the inductor is 0, only when the current through it is constant. So once there's current, you can the inductor can still store energy in form of magnetic energy. And the third characteristic is that it is impossible to change the current through an inductor by a finite amount in zero time, for this requires an infinite voltage across the inductor. So an inductor resists an abrupt change in the current through it in a manner analogous to the way a mass resists an abrupt change in its velocity. So an inductor resists an abrupt change in current. That's why they make as good current regulators in a circuit board. So that's their one of their main purposes. So let us solve a sample problem that involves inductors this time. So we need to find the current IL, as you can see in the diagram. We also need to find V sub C, the voltage across the 4 farad capacitor, the energy stored in both the capacitor and the inductor. So the first thing again that we will do is to open circuit the capacitor, because this sample problem has a capacitor, so we need to open circuit that, and then short circuit the inductor. So that requires us to redraw the circuit diagram. We have this current source, we have the parallel resistor 6 ohms, and then the inductor will be assumed as a straight line, and then we have another parallel resistor 2 ohms, and this time our capacitor rather is an open circuit. So we have over here IL, over here VC. Now that we have redrawn the circuit, considering the open circuit and short circuit characteristics, we can solve the current through we can solve the branch currents. IL is actually the current across the inductor. So just to replace the symbol for IL. So since this is an open circuit, our IL then is the current at I2. So we have I2 is equal to our IL. So we need to solve for the current I2 then. So we can solve this since we have two parallel resistors and a and a current source. We can solve this by current divider. By current divider, we have I2 is equal to 10 amperes, which is the main current, multiplied by the resistor across it, which is 6 ohms, divided by the sum of the two resistors, 6 plus 2. We have I2 is equal to 7.5 amperes, which is also equal to our IL. Now we have our first answer. As simple as that. The next thing to solve is to calculate the branch current and the parallel voltage. So since we have the branch current already, so I'm just gonna write the steps. Calculate branch currents and parallel voltages. So we already solved for IL, so this will be important in order to solve for the parallel voltages. So in the diagram, V sub C or VC is obviously across the 2 ohm resistor. So we need to find the voltage across the 2 ohm resistor, and we can definitely find that using the current and the resistance value. We have V2, which is equal to VC in this case, is equal to IR is equal to 7.5 amperes times the value of resistance, which is 2 ohms. Then we have V2 is equal to VC, 7.5 times 2 is equal to 15 volts. That's our second answer. Very easy. Then to solve for the power, calculate energy. So in order to not get mistaken, I'm just gonna replace it with letter E. We have E for inductor, E sub I and D. Inductor power is equal to 1/2 Li squared. Recalling from this formula, and equal to inductance of 6 henries times 7.5 amperes squared. Then our energy for the inductor is equal to 168.75 joules. So we have our third answer. Simple as that. Don't forget the units. And now we have the energy for capacitor, 1/2 CV squared. Very easy to remember these formulas. We have 1/2 capacitance of 4 farads times the square of the voltage across it, 15 volts. Energy for capacitor is equal to 450 joules. So there you have it. The 4 parameters that we have solved in this sample problem. Our final topic for this lesson is to solve for capacitors and inductors connected in either series or parallel or both. So you won't just encounter capacitors and inductors as standalone loners. They are often connected with other elements of their kind, either in series, parallel, or both. So just like resistors, capacitors and inductors can be simplified in a circuit diagram by adding them either in series or parallel. So the matrix below applies for the series and parallel sum. In this table, we have a guide for how we should add capacitors and inductors in series and parallel. But let's start with inductors, because the way that we add inductors either in series or parallel is very similar to how we add to resistor networks. So inductors connected in series, they can be added in a very plain manner. So LEQ is equal to L1 plus L2 as many inductors in series. And inductors connected in parallel will have the parallel sum, such as similar to resistors. So we have 1 over LEQ is equal to 1 over L1 plus 1 over L2, so on and so forth. But when we move to capacitors, they are in reverse. So capacitors connected in series will be added in a form of parallel sum, while for capacitors arranged in parallel, they will be algebraically uh, added, like a plain addition of all the capacitor values. So I hope that you can notice that the capacitors and inductors are just in reverse in terms of how they are added or how they are simplified. And to show this in a particular sample problem, we have capacitor simplification. So you can see in this diagram we have 4 capacitors, we have 1 voltage source, but instead of simplifying the capacitor network, the problem asks us to find all capacitor voltages. So that's a bit of an extra. So the way that we approach this problem is very similar to the resistor network simplification that we've done from previous lessons, like lesson 3, I guess. The first thing that we will do is to find the equivalent capacitances, which we will represent as CEQ. Let me move that over here. We have to find the equivalent capacitance. So from this diagram we can easily add, we can simplify this first. This will be our CEQ1, and CEQ1 is equal to the parallel sum of these two capacitors. We have 60 microfarad times 30 microfarad over 60 plus 30, and their parallel sum is equal to 20 microfarads. Now we can solve for another step higher to the simplification. We have here combining that with the parallel capacitor, and we will call that our CEQ2. So our CEQ sub 2 is equal to the series sum of 20 microfarad plus 20 microfarad, which is equal to 40 microfarad. The next thing that we can do is to simplify this further to the last remaining capacitor, which is the 40 microfarad, the nearest capacitor to the voltage source. And we don't need to label that as our CEQ3, because that ultimately becomes our final equivalent capacitance. So we have, because they are in series, we have to do a parallel sum for 40 microfarad times the 40 microfarad capacitor on top over 40 plus 40, and the equivalent capacitance is 20 microfarad. So we have the equivalent capacitance of the capacitor network. What we can do next, our step number 2, is to solve for the equivalent charge QEQ, which is equal to equivalent capacitance CEQ times the voltage source. So why is this so ugly? QEQ is equal to the CEQ of 20 microfarad times voltage of 150 volts, and our equivalent charge is equal to 0.003 coulombs, or letter C. That's how we represent our charge. Then our third step would be a couple of reiterations for step number 2, as well as solve for individual charges Q. No, to solve for the capacitor voltages from the formula Q is equal to CV. Now, going back in this diagram, we can solve for V1 first, since it is the nearest. We have V1 is equal to Q over C is equal to Q over C sub 1, the first capacitor. And our Q of 0.003 ohm coulombs will be divided by 40 microfarad. So our V1 then is equal to 75 volts. That's our first voltage, first of 4 voltages. Now we can solve further for V2. So our V2 is the voltage for capacitance CEQ2. So over here, so we will use that as our capacitance. V2 is equal to Q over CEQ2, because as you can see in the diagram, it clearly represents the voltage across that capacitor. So we will use 0.003 coulombs again, this time divided by, again, 40 microfarads. V2 is nevertheless 75 volts. That's our second voltage. 2 out of 4 voltages solved so far. Now, moving on to V3 and V4, we can look at simplifying expanding the capacitor network again. So we have to acknowledge that since V2, as you can see here, V2 is equal to the sum of V3 and V4. We have to acknowledge that V2 is the sum of V3 and V4. As you can see in the diagram, they are immediately in parallel with V2, the voltages V3 and V4. CEQ1, or yep, the first this CEQ1 will have V2 across it. So we will use V2 for CEQ1 in order to solve for the charge for CEQ1 for the combined capacitance. I'll just solve for another Q with a single apostrophe equal to CEQ1 times V2 is equal to 20 microfarad times V2. Our V2 is 75 volts. Our Q then is equal to 0.0015 coulombs. Now we have to note that capacitance in series have the same charge through it. So it's basically saying that in a series connection, if it were to be resistors in a series connection, the current is equal all throughout. And the same concept is true for capacitance, only that it deals with charge, and capacitance in series will have the same charge through it, which means that we can solve for V3 and V4 for the 60 microfarad and 30 microfarad capacitors in the circuit diagram using Q apostrophe. We have V3 is equal to Q over C3 is equal to 0.0015 coulombs over 60 microfarad. Our V3 is equal to 25 volts, and our last voltage V4 will also use the same charge over C4. We have 0.0015 coulombs over 30 microfarads. V4 then is equal to 50 volts. And now we have solved for all the voltages across all capacitors. So I'm just gonna box it for emphasis. Now, moving on to another type of problem that involves inductors. So this one's pretty easy, since inductors will be treated in the same way as resistors are. And the problem asks us to simplify the inductor network. So this is really similar to simplifying resistor networks. The first thing that we can add is this network over here. We have LEQ1. LEQ1 is equal to the series sum. We have 40 millihenry plus 20 millihenry, that is equal to 60 millihenry. The next thing that we can add is this network over here, which we will call as our LEQ2. So our LEQ2 is a parallel sum. We have the parallel sum of LEQ1 60 millihenry times the new inductor 30 millihenry over 60 millihenry plus 30 millihenry. We have LEQ sub 2 is equal to 20 millihenries. Then we can add LEQ2 with this series inductor, and we call it LEQ3. LEQ3 is just a series sum. We have the LEQ2 20 millihenries plus 100 millihenries in series to it. We have LEQ3 is equal to 120 millihenries. And then we have another inductor in parallel to it. We call that our LEQ4. It becomes really messy. LEQ4 is a parallel sum between 120 millihenries LEQ3 and 40 millihenries in the diagram. So parallel sum of these two inductors. Our LEQ sub 4 then is equal to 30 millihenries. Next is when we connect this in series to this inductor. So we will do a series sum LEQ5. No. LEQ5 is a series sum between LEQ4, which is 30 millihenries plus 20 millihenries, and that is equal to 50 millihenries. Then finally, our main LEQ, which is in parallel to LEQ5. So that's our main LEQ. We have a parallel sum of LEQ5 50 millihenries and 50 millihenries plus 50 millihenries. Our LEQ is equal to 25 millihenries, and that's the value of our simplified inductor network. Very easy and very familiar to you. So if you have any questions for this lesson, please don't forget to send me an email or chat me using Google Hangouts and Google Chat, or just leave a comment on our Google Classroom in order for other students to follow on the discussion. And I hope that you will be more curious in solving this sort of problems. You can do some practice problems from the textbook, and your assessment on this lesson will follow next. Thank you so much and stay safe.